we've been able to actually now figure out how far away vast numbers of galaxies are from us and build up enormous three-dimensional maps of the cosmos. And I had a great fortune and luck in my career to get to work on the Sloan Digital Sky Survey that you see here, which is one of the most ambitious three-dimensional sky mapping projects to date. And again, we've learned that everything we thought existed, now our galaxy, was just a part of an even grander structure. Groups, clusters of galaxies, superclusters, and even enormous filaments like the Sloan Great Wall stretching 1 billion light years. And even this is still not the end of space. Even this is still part of an even grander structure, what we affectionately know as our universe, the spherical region of space from which light has had time to reach us so far. Now, the exciting thing that you see here is that this ant can actually figure out whether it's on a curved surface or not without going all the way around, by just drawing a triangle. If he sees that the angles add up to more than 180 degrees, like he learned in his ant high school, then it's curved. And I've had a lot of fun with my friends and colleagues doing exactly this experiment in our physical space, making the biggest triangle you can imagine, which goes from Earth over to the end of the edge of the universe, off to the side and back. And the most accurate measurements we have show so far no hint of any departure from 180 degrees for the sum of the angles. So we have no evidence there that space is not infinite. In summary then, we've repeatedly underestimated both our ability to understand the cosmos and also the sheer size of it. And the edge of what we saw here in our explorations of space is the edge of our observable universe. But what is the deal here? What are all these red, yellow, and blue spots that adorn the edge of what we can see? To understand this, it's not enough to just talk about our place in space. We also have to understand our place in time. We saw that as we explored farther and farther out into space, the farther we looked, the more stuff we found. Very intuitive. But finally, beyond all these beautiful galaxies, we saw that the edge of what we could see, the edge of this spherical region that we call our universe, beyond all of these galaxies, we're going to see a plasma screen of hydrogen plasma. And that's opaque. So it's going to look to us like there's an opaque wall there of plasma. And it's going to look that way in whatever direction I choose to look. I'm going to see galaxies, and I'm going to see nothing, and then there's going to be a plasma screen. So it looks to us actually like we're surrounded by a spherical plasma screen that we're looking at from inside. And we can, and we in fact have, photographed this with these beautiful, and gotten these beautiful images from the Wilkinson microwave anisotropy probe. These are remarkable pictures of these are baby pictures of what our universe looked like just 400,000 years after our Big Bang. 13.8 billion years it took the light to reach us here. Okay? Did they get it right? And yes, look how well they agree. It's just fantastic. Except now it's an even sharper image. It's really spectacular that we've been able to get this sort of images. These are photos of the most distant thing you can photograph in science. Now, another striking thing about these images is they reveal that the baby universe was very boring, because the color scale here has been stretched by 5 or by 10 to the 5 for you to even see anything. It would look gray otherwise, or uniform. What's shown here is simply how hot the plasma screen is in different places. And it differs by only 0.001% from place to place, which means that the plasma was only 0.001% denser in some places than other places. That's about as uniform as the air in this room. I mean, raise your hand if you can hear me.
So we want to imagine a thought experiment of having a spherical shell of matter, empty inside, just a shell on the surface. And I need to know what the gravitational field of that looks like. And it was calculated by Newton. It's in his Principia. So I'll just tell you the result. Many of you, I'm sure, know this. And if you don't, you'll just have to believe me. The result is that outside the shell, the gravitational field is exactly what it would be if the whole mass of the shell were just a point mass at the origin, just a 1/r² force. So these force lines shown outside are supposed to represent that. Inside the spherical shell, the gravitational field is exactly 0. It cancels out in the different directions. So the sum, when you add up the force due to the attraction to each bit of mass around the shell, adds up to exactly 0. And Newton figured that out, too. So now what I want to do in my thought experiment is to imagine that this shell is made out of something flexible, putty of some sort, clay, so that I can allow it to collapse under its own self-gravitational force. There'll be a force on the shell pulling inward. Every particle in the shell will be pulled by the other particles of the shell, and the net force will be inward on any particle of the shell. So I want to take advantage of this inward force